This video is the last in the 12-part series all about calculus from the point of view of a physicist. And in this video, we're going to look at how to construct your own differential equations. We're going to go through an example of how to solve a differential equation. And then we're going to look at a few more examples of where differential equations appear in physics. So the basic approach to dealing with differential equations is first of all to identify the variables involved in your problem. Then you construct your differential equation from those variables and considering how those variables interact with each other. What do you think the rates of change are? Then you have to solve the differential equation. That's the tricky bit. And then finally, you've got to make sense of the solution. So the example we're going to look at is where we drop a mass through air. And very often in physics, especially at GCSE and A-level, you will assume that air resistance is negligible. Well, here we are going to have a situation where air resistance is not negligible. There are different approaches to dealing with air resistance. How does air resistance vary with velocity? Stokes' law, which is for spherical bodies moving reasonably slow speeds, but Stokes' law says that the air resistance, or fluid drag, viscous drag, is proportional to the speed that a body moves through the air, or the fluid. But that's not necessarily the best model to use for air resistance. And if we consider a skydiver falling through the air with their arms and legs flailing about, then Stokes' law definitely isn't going to be the right solution to use. But we need a starting point. We're just modeling a situation. So let's say that air resistance is proportional to speed, and we'll take it from there. Our resultant force could be written like this. The weight of the body, mg, acting down, minus, because it's in the opposite direction, the air resistance, so it's acting up, and that is proportional to the speed of the body, so I've said that that is equal to some constant times v. Now, all of that is the resultant force, so it gives rise to a resultant acceleration. The resultant force is mass times that resultant acceleration. By definition, our acceleration of our body is the rate of change of velocity. So we can substitute this into this equation before, and we get this expression here, that the mass times the acceleration is equal to the weight minus the viscous drag, but acceleration we've replaced with dv by dt. Now you'll notice this equation has a rate of change and the v here as well. It has both the rate of change and the variable. So we considered the variables, and then we put them together, we've constructed our differential equation. And I'm just going to divide through by mass. And that gives me this equation here, which I'm going to call equation 1 for now. This is our differential equation. This is what is called a linear first-order differential equation. It's linear because the v term here is not squared or raised to a negative power or anything like that. It's a linear relationship, and it's a first-order differential equation because of this term here. D by dt means it's first order. If that was d2 by dt2, or should I say d squared by dt squared, that would be a second order differential equation. This is a first order one. So what we do is we open our big book of how to solve differential equations and look up a solution. Now there are far too many solutions to different types of differential equations for me to be able to go through that in a small little video. Indeed, I don't know them all. You can study for months, for years, all these different ways of solving all sorts of different differential equations. So I'm just going to present you one solution here, which I looked up, and that's how physicists work. If you want a solution to an ordinary differential equation, or even a partial differential equation, we look it up. We look up a general solution and then apply it to our situation. And we leave it to the mathematicians, who are far cleverer than we are, to decide how all this works. So, to solve this equation, and this is a bit of an odd thing to do, but go with it, we invent a new function. The new function, v, is alpha multiplied by beta. Now, in the solution I looked up, it used v and u for these two new functions, but I've used v for my velocity, so that's no good. I might want to use n and m, but I've used m for my mass, so that's no good. So perhaps I should use A and B. But A is my acceleration, so that's no good. And I don't want to use I and J because that could be confused with either unit vectors or imaginary numbers. So I was running out of letters. Maybe I could have used P and Q perhaps. But no, I've decided to go with alpha and beta because I know I haven't used those anywhere in this situation. So don't be spooked by the Greek letters. I just needed two more variables. So v, which is a function of time, is a product of these two functions of time, whatever they are. Now, it could be that b is just the number 1, and alpha is in fact v. That's a possible alpha and beta that would make this equation work, but I hope you can see there are all sorts of other possible solutions where alpha and beta, when multiplied together, would make the function v. Loads of different solutions, but by choosing this arbitrary equation here, it means I can use the product rule that we learnt about earlier. So here is the product rule, and I'll put a link to the video where I derived the product rule in the description below. Here's the product rule for differentiation. dv by dt, that's this function here, is alpha d beta by dt plus beta d alpha by dt. Now this is equal to dv by dt, and this is equal to dv by dt. So we can equate them. And when we do that, we get this equation here, where this is from the second part, and this is what we had from the first part. But you'll notice that instead of v, I've replaced that v with alpha multiplied by beta. That was that substitution we mentioned earlier. So this whole term here is just dv by dt, but the way it differs is that instead of having k over mv, I've got k over m multiplied by alpha multiplied by beta. So then what do I do with it? Well, I gather my like terms together. I gather the terms with an alpha in them over to the left-hand side. And note it's just the alpha terms, not the term here with d alpha by dt, just the alpha terms. I gather those to the left-hand side, and any terms that don't have just alpha in them end up on the right-hand side. So this term has ended up over here, and this term has ended up over here. And I do that so that I can factor the alpha out and get this term here. Now, according to the solution I looked up, we can set the part inside this bracket to be equal to 0. And I had some trouble with this. I thought, how can you justify that? But it's entirely possible that I could carefully choose my beta function so that when I differentiate it, add it to this term here, it equals 0. There's no reason why I couldn't pick special beta functions that make that true. So that's what I do. So this term, which was in that square bracket, I've set equal to 0. And then I've added the k beta over m to both sides. And that gives me this equation here. Now I can solve this equation. I can solve it in the same way as I've solved things before. If I divide through by beta and multiply through by dt and then integrate. And that's exactly what I'm doing down here. So the left-hand side I've divided by beta, so I've got d beta multiplied by 1 over beta. And the right-hand side I've multiplied through by dt, and then I've simply integrated everything, adding up all those small increments of dt and d beta. Now I know what the solution is to the integral 1 over beta d beta. That's the natural log of beta plus some constant. And this term here, well, minus k over m is a constant. So this is the integral of dt, which is just t, plus a constant. So I combine those two constants. I've just called it c at the end here, as some constant. So now what I want to do is get this into a sensible form where I have beta equals. I want beta as the subject. So I raise e to the power of that equation. E to the power of natural log of beta is just beta. It's the laws of logs. And e to the power of this mess here is e to the power of c multiplied by e to the power of minus k over m t. And because that's because these are added together, that's how the laws of logs work. Now when t equals 0, beta equals EC, or should I say EC equals beta. So I've called e to the power of c beta 0. This is where it gets clever. I've found my particular beta function that gives me that solution, that bit in the square brackets is equal to 0. I found what that beta has to be. So now I can plug that back into the right-hand side of that equation I had before. Remember, this bit here was 0, and this equation will all work. I found what that function of beta has to be. So let's plug that beta in here and see what happens. This left-hand side, because this term is 0, is equal to 0. But this right-hand side, where I've substituted this beta, becomes g minus, instead of beta, it's beta naught e to the minus k over mt, multiplied by d alpha over dt. So I'm going to do a few steps in one here. I multiply through by minus 1. I then subtract g from both sides and then divide by beta 0 e minus k over mt, and it gives me this expression at the bottom. Oops. This expression at the bottom here. And you can go through those steps step by step if you want to follow that. But it's pretty straightforward algebra to get from here to here. I'll say it again, multiply through by -1, subtract g from each side, and then divide through by this term here, and you get this here. Okay, next we're going to multiply through by dt and then integrate. And that's what I'm doing here. Now, the right-hand side here should be quite straightforward. Integral of d alpha is just alpha plus c. The left-hand side here, well, we know how to solve this, don't we? We've seen this in an earlier video. This part here is just a constant, so that can come outside the integral. And so we've got this factor multiplied by t and e to the power of that. Well, when we differentiated e to the power of nt, it became ne n to the power of nt. So what we do is the opposite, because we're integrating, we go in reverse. So instead of having the coefficient as k over m, the coefficient is m over k. And that makes sense because integration and differentiation are inverse functions. I think integration was called the antiderivative. So we end up with this expression I've highlighted here. Now we can set alpha to be the subject by subtracting through by this constant of proportionality. And of course it's a constant, so whether it's plus or minus, I really don't care. It's just a constant, some arbitrary constant. So I've just written it rather lazily like this. Notice I've changed the order of some of these letters around, but that doesn't really... Okay, so first of all, we found a function for beta, which was beta 0 multiplied by e to the power of minus k over mt. Then we found a function for alpha, which was just done. That's this term here. So what we can now do is multiply this bracket out. Now the first term we multiply out is this mg over beta naught k e to the k over mt. We multiply that by beta naught e to the minus k over mt. You'll see that the e to the minus k over mt cancels. And it looks like I made a little mistake here as well. The beta also should cancel as I multiply this out. So that would disappear as well. There we go, that's better. So now I've got mg over k as this term here. The second term over here is just multiplying out this part here. Here is our expression for velocity as a function of time. We've done it, we've got it. It's some value here plus something here. Now let's have a look at two particular cases. One where t is 0, in other words, our initial state, our initial conditions. When t equals 0, the velocity should equal 0. We should have 0 initial velocity. Well, when t equals 0, e to the power of minus k over mt becomes e to the power of 0, which is 1. And so our expression for the velocity just becomes this. Notice we want the velocity to be 0 initially. We're letting go of an object with an initial velocity of 0. And I could probably put a minus in here, but again, these are just arbitrary constants, so I'm not bothered about the sign on them. I can worry about that later. I've got an expression here. The second condition we can look at is what happens after the object has been falling for a very long time. So as t approaches infinity, we want the velocity to approach the terminal velocity, whatever that is. But as t approaches infinity, this term approaches 0. And so as this term approaches 0, the velocity, which is now the terminal velocity, approaches mg over k. We can rearrange that. I don't need to. I can just swap it around. So it's mg over k is equal to vt, the terminal velocity. Now the equation on the left is equal to mg over k, and the equation on the right is equal to mg over k. Therefore, the equation on the left is equal to the equation on the right. And this is going to be helpful for choosing what these constants should be, what constants c and beta naught and vt, how those constants all relate to each other. And so here's the last step, you see, our final equation. The velocity at a time t is going to be equal to mg over k plus c beta 0 is vt, the terminal velocity, multiplied by e to the power of minus k over mt. There it is. That's the solution to our differential equation. That is an equation for velocity as a function of time, something we can use. And if we have a look at what that function looks like using Desmos, it looks a bit like this. So what can we see here? Well, we've got our equation at the top. I've just typed it in exactly as we derived it. We've got here the mass. Let's say we've got a 90 kilogram individual. maybe it's a spherical body falling through the air. We've got g, the acceleration due to gravity. Let's call that 9.8. It's minus because it's downwards. And then we've got vt, the terminal velocity, which we've chosen to be 55 meters per second. So with those conditions in place, we can have some value of k that we can choose, like this. Now, some value of k will give us that terminal velocity of about 55. That suggests to me there might be ways of simplifying this even further. I don't know. Maybe vt depends on k somehow. But look, I've got a graph of velocity versus time. It looks reasonable. It looks sensible. Falling for about 30 seconds, we start moving at this terminal velocity, which about 55 meters per second seems reasonable. It's a model, and we could fiddle with the numbers to make it more accurate. But it's a model. It's a mathematical model of a body falling, and we've taken into account air resistance. Now, next steps for this might be to do some dimensional analysis to work out what k represents. Maybe pick some sensible values for k based on the physics, not just modeling what we observe. But there we are. That's a good starting point. We might also want to go back to that initial premise that air resistance varies linearly with velocity, and maybe try out something different. But then we would end up with a non-linear ordinary differential equation to solve, and that needs to be solved in a different way. And again, you would look up how to solve that. So let's have a look at a few examples of where differential equations appear within physics. I'm not going to go through the solutions of these. I'm just going to show you just a few examples from different areas of physics that I learnt about a long time ago and have probably forgotten about. So here we've got a capacitor, and it's connected in a circuit with some power supply and some resistor. There's a voltage across the capacitor. We know from Kirchhoff's second law that the EMF we gain here is going to be equal to the potential difference dropped across R, which is IR, and the potential difference across the capacitor, which I've labelled here with V. So that means we have this expression here. Now we know that the charge stored in a capacitor at a voltage V is equal to CV. We can rearrange that to get V as the subject, so we can substitute that into our equation. We end up with this expression here. It's just Kirchhoff's second law and the definition of capacitance thrown in. Now, I is a function of time, because as the capacitor charges, the current is going to reduce over time. And I also know that I is defined as dq over dt. So I can substitute that in. When I do that, I end up with this equation here, where I've just written the I and the R the other way around because R is a constant. So now you can see that Q, the amount of charge that is flowing, is a function of time. Now, solutions to this equation you can derive in all sorts of ways. And you can derive things like the voltage across the capacitor using calculus. And if you say you are charging up to a potential difference equal to the EMF, then we can say that the charge stored is going to be equal to this expression here, where we've just substituted the voltage for this expression here, where our charge stored is now a function of time. And that's quite straightforward to do. So that's a solution to this differential equation here. But does it work? Well, the only way to find out is to plug it in and see if it works. And so the next steps is just me doing that. I'm just plugging it into this differential equation. So here I've multiplied out this bracket and then differentiated it with respect to t, and I've ended up with this expression here. That's a constant, so the rate of change is 0. And this is what you get when you differentiate that exponential function there. Well, that's just equal to that. So we're differentiating this here, and so that's equal to this. And you can follow those steps through yourself. Now, when we plug that dq by dt back into that equation we had before, that differential equation with dq by dt in it, we get this expression here. And if this expression here is true, then the left-hand side should equal the right-hand side. Well, in this case, it's pretty bad practice. It equals 0. So if we work through it, we end up with 0 equals 0. Is that a proof? Well, maybe not, because you end up with 0 equals 0 by making a mistake somewhere as well. But no, in this case, that is a solution. And clever people can work in reverse to get to the capacitor discharge equation in a different way, knowing this. But it's not all capacitors. There's a component called an inductor, which you may or may not have heard of. An inductor works like this. It stores energy in the magnetic field. And it means there's a rate of change of current in this coil. And the proportionality, the constant of proportionality between the rate of change of current and the potential difference across the coil is called the inductance, which we get that letter we give that the letter L. So according to Kirchhoff's second law, we should have the same EMF gained as the voltage we drop. And of course, I've just substituted that in there. And there's a differential equation that we can try to solve in our usual way. Look, it's got an I here and a di by dt. That's a linear first order differential equation. And we've looked at how to solve one of those today. So you could use the same techniques to try to solve this equation. But here's another example, LRC circuits. When you've got a capacitor and an inductor and a resistor within the same circuit. In that case, we're going to use Kirchhoff's second law just as we did last time. This is the EMF across the inductor, this first term. This is the EMF across the capacitor, the last term. So this is the voltage dropped across the inductor. This is the voltage dropped across the resistor. And this is the voltage dropped across the capacitor. And it all equals 0 according to Kirchhoff's second law. We know the definition of current, so we can substitute that in here, and we end up with a second order differential equation, which actually looks quite similar to a damped harmonic oscillator. All of this stuff is first year university level physics. So I'm not going to go into it in this very short video, but I'm just showing you how these differential equations crop up again and again and again. One of the most famous examples of these differential equations cropping up is Maxwell's equations, which come from Gauss's law for electric fields, Gauss's law for magnetic fields, Ampere's law, and Faraday's law. And a solution to Maxwell's equations here gives rise to, a solution to this gives rise to these sinusoidal variations of electric and magnetic field with the same frequency and the same wavelength. K is the wave number, it's 2 pi divided by the wavelength. But okay, I'm going far too advanced really. Just trying to show you that these differential equations, you can construct them by just thinking about what the variables are doing, and then you can solve them to find solutions that you can then make sense of physically. That's the approach we follow. And with that, it's a full circle back to the start, identifying the variables, constructing the equation, solving it, that's the tricky bit, and then interpreting what you've got.